So, next thing, you will want your formula sheet and a graphing calculator. Today we're going to do some shortcuts on the calculator. So we just got done calculating a bunch of probabilities, and this is still related to that, but we're going to get into some different probability distributions now, where we're doing less of actually finding the probabilities and more of like finding the average and things like that. So kind of back to our mean and standard deviation stuff, except with a probability distribution. So first thing, we just have some definitions. Today we're talking about discrete variables. So we did discrete and continuous back at the beginning of the semester. Do you remember the difference between discrete and continuous? Yeah, the continuous we can't count. It has all the decimals. Discrete is countable, like 0, 1, 2, 3, 4. So, a random variable is just a numerical measure of the outcome. We're looking at discrete, so a finite or countable number of values. If it's continuous, there's an infinite number, and we're not getting into those yet. So we're looking at only the things where we could list out all the possible values. So first, I want to be able to look at data and decide if it's discrete or continuous, and what my possible answers might be. So if I ask you to look at the number of light bulbs that burn out in a room of 10 light bulbs in the next year, would that be discrete or continuous? Discrete. We can count the number of light bulbs that burn out. And then state the possible values. So what can x equal? So discrete is countable. First we have to decide, can it equal 0 or not? Could we have 0 light bulbs that burn out? Yeah. So 0, 1, 2. Do we have a maximum number of light bulbs? 10 in this case. So everything from 0 to 10. And you could list them if you really wanted to, but apparently I'm being lazy today, so I just put that. B, the number of leaves on a randomly selected oak tree. So, is it discrete or continuous? Discrete. We could sit down and actually count leaves if we wanted to. Okay, can it equal 0? Yes. 0, 1, 2. Do we have a maximum number of leaves on that tree? No. So all I can say is it's really like 0, 1, 2, and keeps going from there. All right. The length of time between calls to 911. Could that be a decimal? Yes. Anything like a time frame, weights, those things that allow for decimal values, those are continuous. Okay, so when we're measuring those, all we really know is it has to be what kind of number? It has to be positive, right? We couldn't have a negative time. Can you truly have a time of 0? There's always going to be at least a millisecond between when you set the phone down and when it rings again. So all we could really say for those values is it has to be bigger than 0. We can't really list them out. And that'll be the case anytime it's continuous. We're just looking at like an inequality. We won't be able to list them. So today we're specifically looking at these discrete ones. We saw probability distributions back in the beginning of chapter 5. So remember, a probability distribution just listed the possible outcomes and the probability of each. So that is still the case here. When we looked at these, what were the requirements to be a probability distribution? At the end, we had to look at those tables and make sure what was true. It had to add up to 1, and every probability had to be between 0 and 1. All right, so just as a quick refresher of what it looked like, we're going to make up a probability distribution. So suppose a basketball player is asked to shoot 3 free throws. Create a possible probability distribution for the number of shots made. So if you are shooting 3 free throws, you could make 0, 1, 2, or 3 of your shots, right? I did not tell you what these probabilities were, and I didn't give you a formula for finding them. I just asked you to make a possible one, so we're just making up probabilities. So what do you want to say the probability of making none of them is? 20%. Okay, what about 1? What did you say? 0.5. Okay, I've got 70% so far. What's about 0.2? Or, sorry, 2. 0.3. So then what would be the probability of 3? What would that have to be? 0. Why?
Because it's already up to 1.
Because it already added up to 1. Now, could I have made up any numbers I wanted here? Yes, as long as they were positives and they added up to 1 at the end. So remember those probability distributions, those tables there. All right. So take a second, look at each of these and decide yes or no. Would it be a probability distribution? All right, is the first one a probability distribution?
No.
Why?
They're not a 1.
Okay. What about the second one?
No.
Why?
Negative probability.
Okay. What about the third one?
Yes.
All right. Is that okay with everyone? Okay, we could graph probability distributions. The only reason we would probably draw a graph is if we were trying to decide the shape. You know, remember our skewed left, skewed right, and symmetric. So if I asked you to graph this one, I didn't really specify what kind of graph to draw, so we could do whatever we wanted. You can make a histogram. We could even do just a real basic, like draw a line up to the value, whatever you guys like. So my X here represents the number of movies streamed on Netflix, and my Y is my probability. So my X's go from 0 to 5. My Y's, I'm going to count by 0.1. And I'm just going to do a real basic graph. I'm just going to draw a line up to the amount. So 0.06, that will be about here. I'll just put a dot and draw a line going up to it. When X is 1, I have 0.58, so not quite. Ooh, can't draw a straight line though. Two point 22, 3.1, 4.03, 5.01. All right, not a beautiful graph, but we can kind of see it. How would you describe the shape of that? Skewed right. If we drew kind of like in the bell, here's the peak, and we have more points going to the right. All right. Any questions on that? So that's kind of all review stuff. We've seen probability distributions before. We've talked about shapes of things before. Now we get into the newer parts. So the mean of these, actually in comparison to all the calculations we've done, this is a pretty basic one. We have to, what does the symbol mean? The sum. We add up x times p of x. So if I wanted to do that for this distribution, so X is representing the number of prime movie rentals in a week, and then we have our probability. So if I'm doing it by hand, we basically add another column, X times P of X. And so we are just going to multiply the X value times the probability. So I'm doing 0 times 0.06 is 0. 1 times 0.58 is 0.58. 2 times 0.22 is 0.44. 3 times 0.1 is 0.3. 4 times 0.03 is 0.12. And 5 times 0.01. Does everybody know where those numbers came from?
Mhm.
And so then our mean, we just add them up. Did everybody get that for you? I could also ask you questions if I gave you this probability distribution. What if I said, what's the probability that a person rents 2 movies in a week?
0.22%.
Yeah, just 0.22. You're just reading it from here. What if I said, what's the probability they rent 4 or more? Yeah, you would just add those up. So I could ask you to read me these probabilities. So you're just giving you the probability of a given value. All right, is that okay with everyone? Okay. So, in general, a lot of times we are looking at samples, right? Not the entire population. You know, if I looked at this, this probably wasn't taken with all Prime subscribers in consideration. Your book makes this really big deal about how if you were to take a sample and compare it to a population, we know if I take a sample, is the mean of my sample probably the same as the mean of the entire population? No. But what's going to happen as the size of my sample gets bigger? They get closer. Okay. So sometimes, you know, we might have like probabilities. Sometimes I could still give you original data. If I ask you to find, this one gives the number of DVDs rented by 100 selected customers in a single visit. Compute the mean. What would you do? Add them all up and divide by 100. Do we need to work that out? Are you guys okay with finding a mean if I just give you the points?
Yeah.
We did that back at the beginning, right? So this is pretty much related. Your book kind of acts like this is something new, but it's not. We did means back in the beginning when we were just adding up the values and dividing by the total. So that hasn't gone away. What would happen if I took more than 100 customers? If I added it, made it 200 customers, I would get closer to the population mean, which we've seen that before. Okay. So this is really what we're leading up to. A mean is sometimes called an expected value. So when you're talking about a probability distribution, your expected value, the value we would expect to get out, is the mean of that. This is an example where it comes into play. Okay, so maybe somebody in here is going to grow up and be an actuary. It's a great career. You work for like an insurance company and decide based on these risk factors what should their premiums be. Okay, so you would look at information kind of like this. Suppose a life insurance company sells a $250,000 one-year term life insurance policy to a 49-year-old female for $530. The probability that the female will survive the year is 0.99791. So what happens if the person lives the whole year? What's the company do? They keep that premium money. right? What happens if the person dies?
Give it to their family.
They pay out $250,000, right? Now, ultimately, your life insurance company does not want to lose money. So they are going to set this premium so that they are not going to take a loss. Now, does this work if they're only insuring 100 people? No, because if one of those 100 people dies, it wipes out their money. This works if they are insuring a large number. Okay, this is kind of the expected value. So if I want the expected value of this policy, I am asking for the mean. So let's think about it. We can do x and our p of x. Right. My two options here are if the person survives or if they don't. Okay. X is the value to the company. So if the person survives, we said the company makes $530. Okay, what is the probability they get to keep that $530?
0.99799.
Okay, the other option. If the person does not survive, does the company lose a straight $250,000?
No, there's tax.
Well, they pay that much out, but didn't they already collect your check first? So to figure out how much money they actually lose, what would I do?
Subtract the 530.
Okay. And then how would I show that this is a loss for them? It would be a negative. So x is going to be a negative $249,470. The reason it's not a straight 250 is they did collect that premium check before they insured you. So that 530 was not lost to them. How do I find the probability?
The complement.
The complement. They only pay that out if the person does not survive. So that is 0.00209. Okay, so I have now a probability distribution. I have the table of my outcomes and the probability of each. How do we find the mean?
And then add.
We need x times p of x. So if we add those together, we're talking in money. That means the company would expect to make $7.50 for every person they insure. Now, again, that only works if they're insuring a lot of people, but that is their expected value.
I was terrible teacher.
Okay. Any questions about that? The other thing we can do is find the standard deviation. Yeah.
Oh, there you are. Thank you.
These calculations are on that formula sheet for the mean and standard deviation. So there's two different options. The easiest is this second one. So it's the sum of the x squared p of x's minus the mean squared. Alright, so I want to go back and apply this to example 6 and show you how to use that one. 6, I think. So if I went back to this, not 6, 5, about 5. Okay. We got our mean to be the 1.49. If I want I need one more column on this. And that is x squared p of x. Okay, so to get that, 0 squared is 0 times the probability is still 0. Okay, 1 squared is 1 times 0.58 is still 0.58. The next one, 2 squared is 4 times 0.22 will give us 0.88. Do you guys see where I'm getting these? So 3 squared is 9 times 0.1, 0.9. 4 squared is 16 times 0.03, 0.48. 5 squared is 25 times 0.01, 0.25. So then the standard deviation formula is the square root of the sum x squared p of x's minus the mean squared. So we have to add these numbers up. These add up to 3.09. So my standard deviation is square root 3.09 minus, what did we find the mean of this to be? 1.49 squared. Type that all in. So my standard deviation is 0.9327. If I ask for the variance, how do you get that? Variance is just standard deviation squared. So if I'd asked for that, it's 0.8699. We can also do this on our calculator. So I wanted to show you guys how to do that. When we do this, we are going to enter this original data, the x and the p of x, into the L1 and the L2 on our calculator. So list 1 will be the x values, list 2 would be the probabilities. Everybody have that entered? So now we are going to go to stat, calculate. We are going into one variable statistics, but we're going to kind of change something. So my list is L1. Those are my values. My probability is kind of like the weight of it. So our frequency list, we need to set that to be L2. So if you push second and the number 2, it'll set that L2 to be the frequency. And then if we calculate, we get that our mean, x bar, 1.49, that's what we had before. Sigma, standard deviation, 0.9327. So the same things. so we can do these on a calculator as well. Are there any questions? I wanted to give you guys time to work today, so let's go ahead and jump there. On this, let's see. If it says find and interpret the probability, you don't have to interpret, just like we've been doing on all of these. Okay. I would like for you to find the mean and stuff by hand one time, but after that, if it asks for it again, you can do it on the calculator. I don't mind. I think 21, I am going to alter, I'm just gonna take off 21, you need to only do parts A, C, and D. Part B is just asking for a graph, you don't need to make a graph, so you can skip that. And then do either 18 or 21 by hand. Use the calculator for the other.